Hello. Hope you're well. Hope you're doing okay. So the video is me doing explaining the exercises for assignment 4. So let's jump ahead for the first exercise. The first exercise we basically have to first find the minimal cover, um, explain the steps, and find all the candidate keys with the using the closure of attributes. So first let's get ahead with the minimal cover for the first exercise. I can't fully show the relations here, but I have written down the stuff that the solutions. So the first step is basically a splitting rule for the right hand side, meaning for instance, let's say we have a relation of A to BC here. The splitting rule on a right-hand side basically allows us to write it as A to B and A to C, meaning that we can sort of split these two attributes on the right side. We can't do it for the left side though. So as you can see here, I have done it. We have A, B, A, C here, and there's stuff the relations as usual. The second step is basically trying to remove the extraneous attributes on the left-hand side. These are for the relations where whose left-hand side basically have two relations in them. We'll try to see if there are other relations or other attributes in our set that could potentially mean, for instance, here uh, A drive B leads to D. For instance, we try to look for relations in our set that justifies that A leads to B. In that case, we are allowed to remove B here. So as we can see, we have a A to B relation. So here we could just ignore B and write this whole relation as D, as done down here. There is another similar situation here for a E to F, but we can't do it because here A drives E, E drives A, but we can't find sort of relation that would say A leads to E, or E leads to A, or A leads to F, or E leads to F. So we have to leave it here. This is already minimalized. So the third step is removing the functional dependencies. Here it basically means that if we can find sort of a chain from our relations here that would, for instance, let's take A to C here, that for instance, let's say A leads to B, B leads to D, and D leads to C. In this chain we can see that A at the end of the day ultimately reaches C, so we could potentially delete A to C here. So the way that I wrote it down here is kind of confusing and not really correct. So I kind of changed my mind halfway through, but as you can see, if we have A that leads to three different attributes, uh, B, C, and D, so we basically look to see if there are any sort of chains in our set of relations that would potentially mark A to C, D, or B. As we can see here, first starting with A to B, we don't have any sort of other relations that uh, sort of take us from, let's say, A to attribute X to Y, and Y to B. It just ends here. So we don't see any sort of functional dependencies between A and B. Then we move to A to C and D here, which basically, for instance, if say I remove A to C here, we have a relation A to D. D to E and E to C. So even if I remove A to C here, we will at the end of the day have sort of a chain that would connect A to C. So one removal I can do is this. I can also do A to D. As we can see here, if I remove A to D, we can have A going to C and C going to D, which is still the same thing. So here, for my own convenience between these two, I decided to remove the second one, which is A to C here. So moving on with our, sorry, I had to take a little pause here. With our questions. So we took these three steps that would put like at the end of the day lead to the minimal cover. So after all this, we basically reached the minimal cover, which is this of these five components. Now moving on to the closure of attributes, we basically take every single relationship that we have, pick the left hand side of it and try to see how many elements, how many attributes in our data set can be sort of involved to the attribute on the left hand side. So we start with A. As we can see, we do have A to B, so we write B here. We have also D, so we add D. D on its own, it connects to E, so we write E2, and where did I get this? Yeah. We do also have E that it connects to C, which ends here because we do have like also C that connects to D, but we do have attribute D from before from A. So this is basically the closure attribute. As you can see, we cannot take it as the candidate key because ultimately A doesn't lead to having F at its attribute too. So it's no candidate key. We do the same thing with C, D, and also E, which again, as I wrote here for the closure attributes, uh, they can't be the candidate key because, for instance, C doesn't involve A, B, or F as same as D and E, which have the same mistake, well, with same issue. So the only attribute on the left side that is left is basically the combination of A, E. Here we can sort of uh, do it in a way that first we consider which attributes are related to A, then we consider which attributes are related to E, and also consider the attributes that are related to AE. Which, if we write them down, we can see that every single attribute in our database is sort of in the closure of attributes of AE. So we can take AE as our candidate key. Moving on to the second part, we basically have to follow the same steps as before. We do the splitting part, which happens for YXZ down here. Uh, so we separate it into Y related to X and also Y related to Z. We don't have any other sort of a splitting, so we move to the next part, uh, which is the right hand on the right uh, right hand side redundancy. We don't see it in here because again, so basically, sorry, I sort of forgot. Okay, so yeah, for instance, in this let's say part, am I saying? Yeah, sorry, I wrote it like mistakenly here. It should be left hand side. So we basically we want to try to find the extraneous element in this part. So if we look at it, the only sort of suspicious relation that we can find here is the wx to y, but we don't have any sort of relation that would say w to x, x to w, w to y, or x to y. If we have, we could sort of remove one of these, but since we don't have, we realize that it's already minimized. So we move to the next part, which is a functional dependency, which again means sort of if we remove one of these relations, we eventually get that relation through a chain of attributes that are related to each other. But as we can see, we can't really do it in here because let's say set to w, if we say like we want to remove the w, we won't be able to get it through y to x because x doesn't lead to anywhere on its own. We can't have y to z because we're removing z to w, so we don't really have another attribute that will lead to like another attribute here. And same can be said for all the rest. So basically, the set that we have here is already a minimal covers. Now moving to the closure attributes, we have closure attributes, a closure of attributes for z, for y, and for wx. Starting from z, we basically get z to w, and then w on its own doesn't lead to anywhere. So since we don't have x and y in the closure attributes, uh, we can say that it's not a candidate key. Z is not a candidate key. Then we move to the y part. Well, y in one relation is related to x, in another is related to z. So we add those, and also here z is related to w, so we can add that too. So as we have every single attribute of our database for the closure of attributes in y, we can say that y is a candidate key. Same goes for wx, because wx will together are related to y, and y is related to z. So again, every single attribute of our database can be seen here. So we do have a candidate key. So for this part, we have two different candidate keys, W, X, and Y. Moving on to the second part, which is the 3NF decomposition. And also, we have to underline the primary keys based on the following relation. So, using the steps before, we basically have to find the minimal cover. First of all, to construct the 3NF, which is, as I did the steps, is this group name to genre, group name to date founded, etc., etc. Then we can sort of uh, use the closure of attributes to see which ones are our candidate keys. Sorry. So, so yeah. First, we find the minimal cover, and then using the same steps as the part one of this assignment, we try to find the candidate keys. And as you can see, we have the candidate key as a group name and artist name. So these two together sort of shape a candidate key, which using these, we can sort of mm, decompose the main set to two different relations consisting of group name, genre, and date found, which is, if I'm not mistaken, the second relation here is the same thing. And also, we make another relation using the group name super key, uh, group name candidate key, and use it as one primary key here. So I forgot to uh, add the primary key line in this part. So group name for relation one is the primary key, and for relation two, we have, sorry, relation two is the one below. So relation two, we have group name and artist name as the primary keys plus the date joint. And as you can see here, there is no sort of transitive dependencies because both relations, they have their primary key as one of as a sort of a super key from the candidate key that we found before. Moving on to the last question, which is finding the BCNF of the composition. So here we again look for the candidate keys, and I didn't write down the steps here to sort of like redo everything that I've done in the first and second problem. But the candidate keys here are actor ID and role. And also, if we sort of look at the relations here, we see that one of them is basically trivial, which is actor ID and role and movie title, which is a sort of a non-prime key that is dependent to the candidate key. So this is trivial. This relation also is sort of partially trivial. It doesn't violate BCNF because we know that when we decompose a relationship into the BCNF, we have to make sure that uh, the primary, at least like one of the primary key, is a super key gained through from the candidate keys earlier. So for this relation and this relation, we can see the actor ID. I'm sorry for this relation specifically because I made this also another relation. We have the actor ID is basically the primary key in the relation two, which basically is the super key of the candidate key. So everything is okay because this relation is formed again by having a primary key of of the super key type, basically. Now, the main issue with these relations is the first one, which is movie title to release here. This is a transitive and basically a non-prime attribute to a non-prime attribute, which is a total violation of like the BCNF. So in order to do that, we can sort of join these two relations into one, because if we do so, we can again use the actor ID here as the primary key of the relation, which, as I said before, is a super key from the candidate key. And also, the movie title is basically an attribute that we can join these two relations on and come up with the relation 3, which again does follow the sort of the BCNF rules, you know. So these were my answers for the assignments. I just wanted to add like a small note. This line here, it just came up when I was scanning the papers that I wrote on, so it doesn't really mean anything special. It's just like a glitch from the application. So thank you very much for your time and have a great night.